So while we're talking about intermolecular forces, let's pause for a moment to talk about some select properties of liquids that are dependent, at least in part, on intermolecular forces. The first of these that we'll mention is viscosity. So viscosity is defined as the resistance of a liquid to flow. It's commonly measured as the amount of time required for a specific volume of a liquid to flow through a narrow tube. And the higher the viscosity, the slower the flow rate of the liquid. The more resistance, so the slower it flows. We can see this illustrated here at the right for a couple automotive oils. So automotive oils actually are often characterized by their viscosity. We see here two cases, one where we've got SAE 40 and one that's SAE 10. And over the same amount of time, we can see that more SAE 10 has flowed through the narrow tube into the glass. And so there's less resistance to flow for SAE 10, which makes sense given the lower number here that's assigned for it. Now, viscosity itself is dependent on a couple things, and one of them is intermolecular forces, not surprisingly, since that's what we're talking about in this section. And so we can look at this by comparing a few different molecules and their viscosities. So if we look at the simple table here where we've got three different molecules, they all have OH bonds, so they're all going to have hydrogen bonding. And they have polar bonds, so they'll all be polar molecules. And then look at their corresponding viscosities. And viscosity has a number of different units. Here it's simply given as kilograms per meter second. What we'll notice is that if we start here at the top, we have only one OH bond, and then we move to a case where we have 2 or 3. So we're increasing in the number of intermolecular forces because we have more hydrogen bonding present in each molecule. And what we notice is a corresponding increase in the viscosity. So increase in intermolecular forces results in an increase in the viscosity. Now, viscosity is not only dependent on intermolecular forces. It is also dependent on the molecular structure. And by molecular structure, that's best illustrated perhaps by showing this kind of series of simple hydrocarbons, where all we're doing is extending the chain by one carbon at a time. And we'll notice as the chain gets longer, there is a corresponding increase in the viscosity. Now, a small portion of that increase in viscosity can be attributed to the increase in dispersion forces as you increase the molecular weight. However, as your chains get longer and longer, what we start to see a steep rise in the viscosity. And so while decane here might still be a liquid, if we increase several more carbon atoms, we end up getting to a solid. We've increased the viscosity so much. And what is going on here is not just an increase in the dispersion forces, but actually also when molecules are long and linear and have the ability to entangle with each other, sort of like a pot of spaghetti, that entanglement inhibits free flow of the molecules. And so that increases the viscosity of the solution as well. So viscosity is dependent both on intermolecular forces as well as the molecular structure. Another common property of liquids that we should address is that of surface tension. So you've probably seen this with water bugs walking on the surface of water. What exactly is surface tension? Well, surface tension is defined as the energy required to increase the surface area of a liquid by a unit amount. And we can sort of illustrate this by looking at the water bug and then looking sort of at the water itself. And what we'll notice is that many times on surfaces, you'll see water beads that have a curved shape to them. And the reason for that has to do with the intermolecular forces. So the water molecules within the liquid are surrounded by other water molecules. So they're feeling intermolecular forces, attractions in all different directions. And so there's no net pull in a particular direction. However, the water molecules at the surface, because one side has no additional molecules, or any additional water molecules, then we now have an uneven distribution of those attractive forces, and there's a net pull downwards or inwards that's exerted just by the intermolecular attractions exerted on that molecule. And so we have a surface now that, rather than being just flat spread out, bends and is contracted inwards, and there's a certain amount of then tension with that. And we can expand, we can add force or energy present to then bring that back, that curvature back out, and that extends or increases the surface area of the liquid. And that's where we get the surface tension from. So, and again, I guess to say this in a different way, the reason that it holds the water bug is because when the water bug places a foot onto that surface, in order for the foot to go down into the surface, it has to bend that curvature back out flat, and that requires a certain amount of energy. So if you spread out the force such that the amount of force exerted on any particular region is less than the surface tension, then the bug's able to actually walk or skate on the water. The actual surface tension for water can be given in units of joules per meter squared, so that's energy per a unit volume or a unit area of unit of surface area, meter squared, and it's 7.29 times 10 to the second. Now, if we have a different liquid like mercury that has a much higher surface tension, then we're able to place even greater things on the surface without them sinking in due to that additional surface tension. So we have a pool of mercury here, we can actually place a fairly hefty pound coin on that surface without it falling in due to that surface tension. If you had large enough paddles on your feet, you could probably walk across a pool of mercury with no problem. Now, one other select property we should mention is capillary action. So capillary action is simply the rise of liquids up very narrow tubes. And it's illustrated nicely with this example here. So if we have a large test tube shown here, you see that you see the bend in the meniscus, and that is due to forces, which we'll talk about in a moment. But there's not much rise, but as the tube size gets narrower and narrower, you see that the liquid rises higher and higher in that tube. So what is going on in that case? Well, the cause of this rise is adhesive forces, intermolecular forces between the liquid and the tube walls. So why would that occur? Well, if we just look at a test tube, the walls are made of glass, which is generally a silicate, silicon and oxygen bonds. It's polar. And the water molecules then have polar interactions or dipole-dipole interactions, intermolecular forces between the glass and the water molecules. And that causes the water molecules that are right on that surface to adhere to the surface of the glass and try to rise up it to maximize the intermolecular forces. Now, if we have something like mercury, which has stronger cohesive forces, that's the forces between the liquid itself. Adhesive forces are between the liquid and the walls. Mercury, because it has such strong cohesive forces, will bend, rather than traveling up the wall, it will bend away from the wall towards itself. And this also then explains the shape of the meniscus, which is the top surface of the liquid in a tube. So water bends downwards because the liquid at the walls is being drawn up by intermolecular attractions to the molecules in the glass. Whereas mercury, because it has greater cohesive forces with itself than with the glass, mercury is non-polar, whereas the glass is polar, so there's no dipole-dipole forces going on there. As a result, mercury, because it's got those cohesive forces, it actually bends towards itself rather and bends away from the wall itself. And so the meniscus for mercury bends up, whereas the meniscus for water bends down. And so that's a brief summary of some select properties of liquids that are related to intermolecular forces.